Alright, hello everyone, welcome back to our math library playlist. Today we're going to be taking the Shunting-Yard algorithm that we did a pen and paper overview of last time, and we're actually going to be writing the code for it. So I just need to open up my folder here, and then we should be good to go. Alright, let me just get all this ready. Alright, looking good. Hope everyone's week went well. I am almost done with finals. No, that's not true. I still have 3 more finals left. So I may not be able to stream next week, but I hope I will. But it's up in the air based on what I can get done, but I hope to. So yeah, anyway, we'll first start in OneNote again, just because we're going to look at how we're going to structure the code. So when we looked at the Shunting-Yard algorithm last time, the Shunting-Yard algorithm simply took a list of tokens and then just put it in a new notation. It didn't actually evaluate anything. The evaluation algorithm is something completely different. So the process that we're going to follow is we're going to take our string equation and then we're going to convert that into a token list. And this will be through the token parser. And in the token parser, we're going to be looking for several key characters. There's going to be brackets. There's going to be numbers, and then there's also going to be functions, operators, and constants. The reason why the reason why I said those together was because when we have strings, we're going to want to kind of store them in an easy way to determine if we actually found a token or a function or our constant string, so like e and pi. So the way we're going to do that actually is we're going to be using trees, and specifically AVL trees. And we're going to have our tokens here, so let's say we have a sine, cosine is going to be less than it, URST, tangent is greater than that. So something like this, we'll have it in an AVL tree, which is a self-balancing binary tree. So when we do look at a string, so when we say we get 3 sine 5 pi, and then we have another tree for the constant, so pi and then e, something like that. When we look at these tokens, we'll start with the 3, find it's a number, and then we will look at the s and determine, okay, we need to go through the tree and iterate to find a key that matches this string here. So we go to the tree and we look at the root node and we see that that's sine. Now if this was cosine, what we're going to want to do is we're going to compare the substring of length 3 to the sine here, or to whatever the root key is, and we determine that its cosine is less than sine as a string value, so we traverse left and then we compare it to the cosine on the left, like that, and we find it. So then we return this function node as a token. And then similarly, when we look at the pi, we will just compare it to the root key and we see that it's equal, so we return the constant node there. So that's what this is going to look like. So we're going to be traversing through AVL trees to determine, to find tokens. And then from here, from the token list, then we go into our RPN notation. And RPN is done through Shunting-Yard, which we looked at last time. And then from RPN, we go to an equation tree. And we looked at the equation tree last time, which is pretty much this. So we just create a tree for the equation. And then from the equation tree, then we can do evaluation through a post-order traversal. And let me just make sure that's correct actually. Yeah, it's post order, because we evaluate the children first, and then we pass the result onto the root, and then go traverse back upwards. So we start at the bottom and move upwards. And then this will be our result here. And the beauty of storing it in an equation tree is we can also evaluate this many times. So when we inevitably integrate variables into it, we can have another tree for variables like x, y, z, and whatnot, c, all that. Then we can actually reevaluate this equation with several different variables, which will be very important and very useful. Alright, so let's hop into the code. Let me just put my tablet away. Alright, so we're going to start in syutil.h. We're going to write a single function, and then we will actually write the Shunting-Yard algorithm. Alright, so in syutil.h, I want to create a function definition. I guess it's already here. Oh, I probably committed it, but I'm just going to delete this and I'll rewrite it as if it was not there. I guess I didn't delete it from here either. Okay. So yeah, I'm up to date with what the committed code is. So this new function is going to be called, or it's going to return an sy token pointer, and it's going to be sy find element. We're going to pass in an integer an unsigned integer as the initial index of a string. We're going to pass in a string pointer s. So we want to take the character at index I in the string stream that we pass in, and then the list of keys to traverse through will be an AVL pointer, so an AVL tree, and then we will have an integer pointer for the length. So the return length, since we can't return two variables, we're just going to store the length of the found token in this pointer here. So if we find sign, we will set the pointer value, or the value at the pointer, to just 3. Alright, so let's copy this signature. You can zoom in. Or no, that's too much. There we go. Alright, so, and then let's go into syutil.c, paste the signature over. Alright, so let's start here. So we're first going to have a base case, if not list. Then we're going to set the length to 0, so dereference length and set it equal to 0, and then return null. Alright, next we want to compare it to the current key. So compare to current key. To do that, we need to get a string length. So unsigned integer n is equal to the string length of the character pointer list.key. So we have a general AVL tree pointer here, and it can have anything as a key, or any pointer as a key. So we first need to cast it to a character pointer, and then get the string length with that. All right, then we're going to store the comparison value. So int cmp is equal to 0. So next we're going to say here, if I plus n is less than s.size. So we first want to determine if there is room left in the string stream to actually find a token. So have room to find the token. So character C. So the method the way that we could compare it is just say cmp is equal to the string compare of s.str plus I list.key. However, the problem with this is s.str plus I will go from the initial character to whenever it finds a terminator character. And we only want to compare a substring of length n, so to match the current key in this node here. So what we have to do is we have to kind of create a substring and terminate the character or terminate the substring after n characters. So we're first going to store the character at the end, or at the at our temporary end for the substring. So character C is equal to s.str at I plus n. So store end character, or first excluded character. Or this should be I plus n is less than s.size minus 1, right? Wait a minute. Oh, no, this is fine, Yeah. So store the first excluded character. Then we're going to set that character to a null terminator. So s.str at I plus n is equal to \0. So we're essentially creating a temporary terminator. A temporary terminator for the substring. And then we're going to compare the substring to the current key. And then we will just put back the character. So s.str at I plus n is equal to c. So return character to spot. So once again, we're just storing the character at the end of the substring, or at the end of the desired length of the substring, and then we just set that to a terminator so that it becomes a string in the memory. So when we call string compare, once again, it wants to find, it's going to look for a terminator character, and it will find that now after end characters. So we want to compare the strings of the same length. Now otherwise, we will just compare to the end of the string. So compare is equal to str compare at s.str plus I, and then list.key. The reason why we still want to compare here is because just because we have a shorter character, or a shorter substring, there may still be, or just because we don't have enough room, there may still be a character, or a valid token that is shorter than the current one. So for example, if we are looking at our constant tree, so let's say we have our constant tree, which is just pi and then e, and our string is just 3e. So we get the 3, and then now we're at this character here, and we see that it's we want to compare this token to the constant tree. So we start at the root, and pi is length 2. However, this would extend past the end of the string, so we don't want to create a substring, because that would require us to put a terminator outside of the memory allocated for this string, which would be invalid. However, we still do need to compare to any children that it might have, or any children in the root node. So we want to traverse left, and this will compare it based on the string compare function. So we still compare it. Still compare to the end of the string. Alright, and now we would determine what to do with the comparison. So if not comparison, then we found a match. We set the length, the return length to n, so that we can return that, have the length in the, so we can know how many characters to advance, and then we return list.value, which in this AVL tree will be our token. And else if compare is greater than 0 and, or else if compare is greater than 0 and list.right, then we want to traverse right. So return sy find element I, starting at the same index, same string. This time the root of the tree will be list.right, and then the length to return to will be length. And then similarly on the left, else if compare is less than 0 and list.left. We can't just do an else statement because there are more possibilities here. The conditions now would consist of if list.right exists. So if this didn't pass, then it would just go to else, which could be the case where compare is greater than 0 and list.right is null, and then we would still traverse right even though we didn't want to. So in this case, we're going to say traverse left. So return sy find element, same initial character, same string. List.left is now the string the tree to traverse through, and then we still return to the same pointer. Alright, and then if none of these conditions pass, we're going to set the length to 0, and then return null. Alright, so yeah, that's how this tree or this searching method is going to work. We're going to use the structure of an AVL tree to our advantage, which is already sorted, and then use that to kind of find our tokens in logarithmic time, which is pretty cool. Okay, so that is syutil.c and syutil.h. We are done with those files, and now we have we're going to create our main Shunting-Yard files. Or do I want this to... I kind of want to rename all these functions from sy to just eqn for equation because Shunting-Yard is only one step in the process, but there's so many other things, so I might do that later, but for now I'm just going to write it as sy. Alright, so let's create two new files, Shunting-Yard.h and Shunting-Yard.c. Let's start in the header file. Alright, so we will have a few includes. So include dynamic array, or lib/dynamic array. Include lib/str stream, the string stream. Include lib/avl.h. Now and then we also want to include syutil.h. And now we can do our macros. So if not defined, Shunting-Yard.h. Define Shunting-Yard.h. And if. Alright, so like I said, or for I think like the 5th time now, we're going to be storing this stuff in a tree, and we're not going to be able to put all that tree initialization code in the main method, so therefore we need to have an initialization method for the library and a cleanup method for the library. So we have void sy init, no parameters, and then void sy cleanup, no parameters. And this will just set up the corresponding trees and then also clean up the corresponding trees. Alright, now for the actual process. We are essentially going to have one function for each step in this process. So we'll have one for a token parser, one for the Shunting-Yard algorithm, one for the equation, and then one to go from RPN to the equation tree, and then one to evaluate the expression. So we'll start with dynamic array, Parse Tokens. So it's going to return a list of sy token pointers, and we pass in a character pointer string. Then dynamic array RPN, and this takes in a character pointer str. And RPN will call parse tokens using the string parameter. So we don't need to pass in a list of tokens here. We can just pass in the string and it will automatically do that. Then we might also want to, for debugging purposes, return a character pointer from RPN. So we'll have a method that returns a character pointer, a string, and we'll call an RPN string, pass in a character pointer, a string for the equation as well. Then sy token node pointer get equation tree, and pass in a dynamic array RPN. So now we're taking the dynamic array from the reverse Polish notation, so from the Shunting-Yard algorithm, and we are going to put it into an equation tree, which all we need to do for the tree is just return the root node, which is defined in the utility header file here. So it is this one right here. So each token node has a token pointer, and then it also points to a left node and a right node as in a binary tree. And then we will have a double, so double evaluate tree and pass an sy token pointer or token node pointer tree, just like that. And then we also want to have another method to evaluate a token. So sy eval pass an sy token pointer t and double x and double y for the two parameters. X and y, these will be the two parameters for a binary function. For a unary function, you can pass in anything for x and you can pass in your argument for x and then anything for y, it doesn't matter. And then if the token is a constant, then it doesn't matter what you pass in for either of them, because it will not call any evaluation function callback from the token since it is not stored there. Alright, pretty good. Alright, let's copy all of these signatures and then head into Shunting-Yard C. Alright, so in Shunting-Yard.c we'll start with by including Shunting-Yard.h, and then we will have a bunch of other includes. So include syutil.h, include sy or lib/sy functions.h, include lib/stringstream.h. Then for some C libraries, we're going to have include string.h, include standard lib.h, and then include math.h. The math header file will contain callbacks to functions that we will require. Alright, so let's print this, or paste the signatures over. Alright, before we start, I'm going to have a few global variables that we want to be able to access throughout all of these functions. So we'll have two AVL trees, so AVL pointer functions and AVL pointer constants. Once again, these are going to be the trees that we use to store the functions and the constants. Now I also want to have an sy token pointer multiplication token. Now the reason why is because the multiplication token will be used in several different spots. When we do our token parser, we may want to have an implicit multiplication sign added in at some point. So therefore, it would be useful to have this token as just a global pointer rather than having to search through the tree every time, because we don't know where it could be. It may be at the top, maybe at the bottom. So just to keep things simple, we're just going to have the global variable for that token. Alright, we will start with sy init. Alright, so here we're just going to create our trees. So create functions tree first. So functions is equal to avl create empty root, and the compare function will be string key compare. So this string key compare comes from the avl header file, and it takes in two void pointers, and it just returns the string comparison of the character pointer, or the string conversions of those void pointers. So we want to have strings as our keys, so we can sort them as such, based just like this here. All right, I'm only going to put in three functions, or I'll just put in one for now, it won't matter, but then there's going to be plenty more in the commit. So to insert, we want to use our avl insert function. So functions is equal to avl insert, pass in the root functions, the key will be sign, and then for our function token, we're going to use this utility function sy create default unary function. The character name will be sign, and the callback will be sign as well. What's up, Powell? I butchered your name. I am sorry about that. That is, yeah. I suck with pronouncing people's names. It's kind of stupid. Okay. Then we're also going to have our operators. So I'm just going to put all 5 operators down now, just so because I do want to use those in the test. So we will do the addition first. So functions is equal to Avl Insert Functions as the root. Key is going to be a plus sign. The value will be sy create binary function. And we're not using the default arguments because this one we need to specify precedence and all that stuff. And also the type. So the name is going to be a plus sign. The evaluation will be add, which is a function I put in sy functions here. I just have a bunch of callbacks for the basic arithmetic functions here. So that's the callback. The type will be operator because it's not it is a function, but we want to specify that it's an operator. The precedence will be 2 and left associative will be true. Alright, should have 2 parentheses here. Alright, then we're going to do something similar. So I'm just going to copy this 4 more times. Alright, and then we just need the subtraction sign, the multiplication sign, the division sign, the exponent sign, and then just change the strings as well in the function parameters. And then the callbacks will be add, then subtract, then multiply, then divide, and then pow. Pow actually comes from the math library. Alright, the precedence, so these are all operators here, so all 5 of these are operators. The precedence will be 2 for addition and subtraction, 3 for multiplication and division, and then 4 for the exponent. And the last thing we need to change is in the exponent, it is not left associative, so the last parameter should be false. Alright, then as I said before, I do want to have a global variable for the multiplication token, so all we have to do is just take the sy create binary function, call for the multiplication token, cut and paste it into an assignment for the multiplication token. So multiplication token is equal to that call there, to sy create binary function, multiply operator 3 and true, and then we can just pass in the global multiplication token as the parameter to Avl insert for the value to insert. Alright, pretty good. Alright, now we're going to do something similar with the constants tree. So constants is equal to Avl create empty root, and the comparison function will be string key compare as well. And then we want to insert our 2 constants, which will be pi and then the natural base. So constants is equal to Avl insert, pass in constants, then pi is a string, and then sy create token constant string. Oops, misspelled that. The parameters to this will be pi and then the value, which as shorthand for the value we can just do 4.0 times the arctangent of 1. That's just a little trick you can use to get the value of pi. And then for e, we're going to have something similar. So Avl insert constants as the root. The string will be just e, and then the value will be sy create token constant string. And then the name will be e, and the value will just be exponent of 1.0. So we take the natural base and raise it to the power of 1, which just gives us the natural base. Alright, for cleanup, it's going to be simple. We just call AVL free deep on functions and AVL free deep on constants. Alright. Now on to the actual algorithmic stuff. So this is just setting up the trees and all, so we can use these in the tests. Alright, we'll start with parse tokens. We're first going to have a few placeholder variables, or a bunch actually. We're going to have an unsigned integer n is equal to the string length of str. And then we want to put this string into an equation, or into a string stream. And the reason why for this is because we want to use our substring function, which will be easier if we just have it in a string stream. So string stream equation is equal to string stream allocate, and we can pass in the size as n, so it doesn't need to allocate it, or actually, oops, not that. Yeah, I'll just leave it like this. So we allocate the number of characters, so we don't need to reallocate after that. And then string stream concatenate, pass in reference to equation, %s for the format, and then the actual argument will be string there. So we create our equation string stream. Now let me just get some water, I'll be right back. Yeah, I'll be back in a second. Alright, now that we have our equation in a string stream, we can start with our other placeholders. So we will have our dynamic array, ret, which is equal to dynamic array default allocate. So we'll have our return list. And then we want to have some variables to store, or to keep track of the state of the iteration. So we'll have a token type, previous type is equal to else. Then token type, current type is equal to else as well. And then int, or unsigned int object length is equal to 0. Now we're going to have a for loop, so we go through each of the characters. For unsigned int n is equal to 0, or I is equal to 0, I is less than n, I plus equals object length. So each iteration we're going to advance past the found object, which we will update based on what token we find. Alright, now for the loop, we're going to get the character. So character C is equal to eqn.str at I. Then we're going to get an object, so sy token pointer object is equal to null for now. This will just be the token pointer that we allocate, or that we assign something to in this iteration. So we will decide which token to give it. And then object length is equal to 1. That will just be the default length. Now for a few quick checks, we can check for brackets and white space. So if C is equal to a space character, or C is equal to a tab character, or C is equal to a new line, or C is equal to a comma, which can be used in a binary function here, then we want to continue. So a comma does not actually change the way functions or the way the Shunting-Yard algorithm works. All right, then we will have our parentheses check. So else if C is equal to an open bracket, then current type is equal to left parenthesis, and then object is equal to sy create token l paren. Thinking that we could also just have a token. Yeah, we can just have the same token for the left parenthesis and the right parenthesis as a global one too. It doesn't make a difference, because what's the point of creating it several times if it's just the same thing? Yeah, so we will have sy token pointer as a global variable, l paren token, and then sy token pointer r paren token. And then in sy init, we want to initialize these. So l paren token is equal to sy create token l paren, and then similarly r paren token is equal to sy create token r paren. Oops. And then in cleanup, we can simply just call free on these. So free the l paren token, or call the sy free token on l paren token, and sy free token on r paren token as well. Since these are pointers and they are not associated with any tree, so it's simply just going to be, we just want to free the memory there. You know what I forgot to do? We don't have a free method for the equation tree. That'll just come later, I guess. That's fine. Honestly, it might not even do that. I might just want to write the Shunting-Yard algorithm, get up to that today, because this is taking a little longer than I expected. Yeah, we'll probably do that next time. Alright, so left parenthesis, and then after that we also want to check else if C is equal to a right parenthesis, and then we'll do the same thing. So current type is equal to r paren, and then object is equal to r paren token. And then we also want to set the left parenthesis token just to l paren token. So if the character is a left parenthesis, set the current type and then the object to the global left parenthesis token, and then the same thing for the right parenthesis. Alright, so now that we have deduced that it is some other character or token or other special number, we want to say else, because we have several conditions here that will be independent, or that we need to have them structured in a certain way so that the parser actually works. So the first token that we want to check for now is the negative sign. So if C is equal to a negative sign. So there are two interpretations for this. Negative sign can either be a negative, or the dash can either be a negative sign or a subtraction sign. And what we know is that it will be a subtraction sign if there is a number before it, or some right parenthesis before it. So what we're going to say is, if previous type, that's why we have that store up, or that placeholder up there. If the previous type is equal to constant, or previous type is equal to r parenthesis, then we're going to say the subtraction sign. It's a subtraction sign. So current type is equal to operator, and then object is equal to sy create No, I don't want to do this. We have a subtraction token. I don't know what I'm doing. Okay. Yeah, this is just me looking at this in retrospect. We can also have an sy token pointer for a subtraction token, because we will be using that in two places. So just like the multiplication token, we want to initialize that independently. So this is equal to sy create, or just copy the function call that we have over here and just paste that over there. So subtraction token should now be set independently, and then we pass in the subtraction token to Avl Insert. Like so right here. So now we have two global function tokens. Now when we determine that it's a subtraction sign, we can just set the object to subtraction sign, or subtraction token. And then the object length is 1 by default. Alright, now we're going to have another if statement. This is not going to be an else if statement. So if sy char is number, pass in C, and current type does not equal operator. So the logic here is, if the character is a dash, that will return true from character is number because of this condition here. So character is number will return true for negative signs. However, if this negative sign, or if we found a negative sign and we know that the previous type is a constant or a right parenthesis, then we want this to be an operator, and we don't want to interpret it as a number. Therefore, we need to make sure that we have not already assigned something to current type, which would be done right here. So this if statement will only pass if the character is a number, so including a negative sign, and we have not assigned it as an operator yet. Alright, so now we're going to do a pretty straightforward number parsing. So is number. So we have to keep track of decimals. So boolean except decimal is equal to true. Then current type is equal to constant. So if the character, or wait, except decimal should just be C, if C is equal to a decimal point, so a period. Or C does not equal that, because if the initial character is a decimal point, we don't want another one. All right, so then we know it's a number, we're accepting a decimal, and we have a constant here. So we set the current type as a constant. Then we're going to say unsigned integer next I is equal to I plus 1. So we want to go through the string and iterate through the characters until we find a number that is not, or a character that is not a number. So while next I is less than n and sy character is number eqn.str at next I. So we're just going to go through the string based on this index here. Then if eqn.str at next I is equal to a negative sign, then we want to break. The reason why is because we can never have a negative sign after the first character. So we know that this will be a subtraction sign. Hopefully, yeah, it definitely will be a subtraction sign. Because if we break now, we will break out of this loop, return a constant from this current iteration, then the previous type will then be constant. So we know that this character will go into this condition here, and then we know the previous type is constant, so it will be deemed as a subtraction sign. And then if eqn.str at next I is equal to a period, then we want to say if not accept decimal, then break. because we found an invalid character. Since if we have 2 decimal points, that doesn't work, so this is going to fuck up. And then otherwise we're just going to say except decimal is equal to true, since we have found a decimal point. And then outside of the if statements, we're going to have next I plus plus. This should actually be an else if. Alright, so then outside of the loop, we're going to say object length is equal to next I minus I to get the length of the current string that is a number. Now, next we're going to want to, there's going to be another kind of niche case that we want to look at here. So sometimes you might just enter something like negative sine of 55.7 times pi, or times negative pi. So we have to account for the case that this negative sign will be on its own, and we still want to interpret it as a negative sign rather than a subtraction sign. So therefore, we want to implicitly insert a -1. So if the object length is equal to 1 and the character is equal to a negative sign, then we want to implicitly insert a -1. Object is equal to sy create token constant -1.0 float, or just -1.0, not a float because this is double. And the reason why we know it's going to be a -1 implicitly is because we know it's not a subtraction sign. So a negative sign is the only other thing it could be. So this case has to pass here where the object length is 1 and the character is just a negative sign. Alright, then else, we're just going to convert the substring to a number. So object is equal to sy create token constant, or constant, and then the parameter here will be a to f, so we're converting a string to a number, and the string will actually be the substring function. So string substring length, pass in reference to eqn, I, and the length is object length, as we calculated before. Just like that. Alright, so this is pretty cool. This implicit stuff is it took a little bit of reasoning to get through the cases, but this is since we know it's not a negative sign, once again we know that this will be a -1. Now you might be wondering, well, why don't I insert a multiplication sign? Well, that case will be accounted for when we look for a function. So we will look at that in a second. Alright, now go back to the if statement. So if sy character is number and current type is not equal to operator, then we want to do an else statement on top of that. So otherwise, it is not a number, or it is not a numerical character. So it's it's a alphabetic character. Or alphabetic character? That's not a word. It's part of the alphabet. Or it's just it's not, or fuck, I don't know. It's not a number. That's all. Could be a constant, but it's not a numerical character. All right. So we're gonna we know not a numerical character. So we're going to want to go searching through the trees. So object is equal to sy find element. We will start with the functions tree. So we start at index I. The string stream pointer will be a reference equation. The list will be functions. So we want to go through the functions tree. And then the length to store it in will be object length, which is our variable that we have up here. So if sy find element returns something, returns a token, then we know that the object length will be greater than 0, so we found a function. So we need to have an if statement here, so if object length, then we found a function. So current type is equal to object.type. And object.type will be based on whatever the token it returns is. Now otherwise, we want to search through the constant tree. So it's going to be the same sort of thing. Object is equal to sy find element. Pass in the parameter I, equation, a reference to. Then the list this time will be constants. Thank you for the kind words, Furkan. And then the length, or the output length, will be object length again. All right, and then we're going to set the current type to constant. And then we want to determine if nothing was found, then we just want to put it as a 0. So if not object length, then object is equal to sy create token constant 0.0, and then object length is equal to 1. Just so because if we set the object length to 0, then it will just add 0, and we will end up in the same case in the next iteration, so it will be an infinite loop. So we just want to set the object length to 1 so it actually advances the character. Alright, now outside of this else statement, we need to have some more implicit checks. So there are going to be a few times when we want to add an implicit multiplication sign. So for example, we are looking at the negative sign of 3 pi. So if we were looking at something like this, we want to add 2 implicit multiplication signs here. Well, there's going to be an implicit -1 from the negative sign. However, that would just become -1 sine of 3 pi. Implicitly, we want this to be -1 times sine of 3 times pi. This is how the token parser we want to pass it in like this to RPN, or to the Shunting-Yard algorithm. So therefore, we will add an implicit multiplication sign if we need to determine if current type is equal to function, or current type is equal to constant. So this will be -1 or the current type will be a sign, which is a function, or pi, which is a constant. Now that I'm thinking about it, oh wait, no, this check has to be here. So this has to be in parentheses, and then we're going to have an and here to determine if the previous type was a constant. So and not previous type is equal to else, or previous type is equal to operator, or previous type is equal to left parenthesis. So the previous type cannot be any of these 3 for this to be a multiplication, or for us to need to, or to implicitly add a multiplication sign. So if the previous type is an operator, then we don't want to add a multiplication sign. If it's a left parenthesis, then we don't want to add a multiplication sign implicitly. Or if it's else, we don't want to add a multiplication sign. But if this condition passes, we're going to implicitly add multiplication sign. So dynamic, so dynamic array, add last, pass in a reference to ret, and then multiplication token. So this is different from doing our implicit negative sign. So with the negative sign, this was the current token. The negative sign was the current token. So we wanted to implicitly insert a -1. We want to do something similar here. However, we don't want to skip over the current token, which is a function or a constant. So we want to implicitly add that multiplication sign to the list, and then add the token at the end of the iteration. All right, so let's go out of all the conditions here, and let's just go into the loop block here. So after the if statements, we're gonna set up some things. So previous type is equal to current type. Current type is equal to else, and then dynamic array, add last, pass in a reference to ret, and then object. And then outside of the loop, we're just going to return ret. Alright, so let's go ahead and test this out to make sure it all works. So I'll delete this stuff here. Alright, or actually I just want to comment this out. Alright, so for our test, we are going to have our string. So we'll have a dynamic array. RPN, or just token list, is equal to parse tokens. And the equation string will just be, I'm just going to put a random equation in here, but I want it to actually to work out here. So we'll have a negative sign of 2 pi space cosine of 2e minus the square root of, oh, okay, this actually won't work. I can actually add these functions, and I'll do that in a second. So the square root of 22, 2 parentheses closing, plus a -1. So this is going to test pretty much all of our implicit functions here. So what this explicitly looks like is a -1 times the sine of 2 times pi times the cosine of 2 times e minus the square root of 22 plus a -1. And in a token list, it should look exactly like that. This is a little dim. I don't know if you guys can see this, but yeah. Alright, and then I just want to print these out. So, how did I print this out last time? Oops, here we go. Alright, so I have a print token function. So void print token takes in a void pointer element. So sy token pointer t is equal to element, implicitly converts. So then we'll have a switch on the type, case constant, print f. We'll just print out the float value here, t.val.constant value, and break. Case function falls into the case of an operator too. In this case, we're going to print a string, which will be t.val.funcval.name, and then break. Then case else, which will print f. I'll just print out null here, and then break, and then default, we will print f %s as the t.val.string value, and then break. However, I think I'm missing something here. Hold on. syutil create token constant string. Okay, so yeah, there is one extra case that we have to have in here, and that's going to be case constant str. So this will also print out a string, and the string will be t.val.named constant value dot name, and then break. Alright, so let's take this and we will iterate through the list. So dynamic array, iterate, pass in a reference to token list, and then the function callback will be print token, and then dynamic array free, pass in a reference to token list. Alright, so let's run this. Or I think I need to add to the build path. Didn't do that. Alright, Shunting-Yard C. And then also in debug.bat, Shunting-Yard C. cd test run. Max is redefined. Where is it redefined? Avl. These are warnings. Okay, so it's oh damn it. That's good. Alright, so let's debug real quick. And we can break at Shunting-Yard.c 66. And then run. Alright, so we have a negative sign. It's good. Alright, so it determines that it should be a negative sign, or that it should be a number here. So accept decimal, current type, good, good. Object length, let me just print this out, is 1. Alright, so it determines that it should be we should add an implicit -1 here. Good. Where's this at? 95. Why did it go back there? Alright, well, alright, good, good, good. Alright, add the object to the end of the list here. Alright, we should... Oh, it's because I forgot to add the other functions. Okay, that makes sense. So I need a cosine and a square root. Got it. Alright, so let me just paste. I'm just simply going to add some two new unary functions here. Alright, now let's run this. God damn it. Alright, so we get a object length. Good, good, good. It's not that. Nope. So we want to find it in the functions. So print object length. Oh, 0. Okay. So it's not finding this then. Oh my... Okay, I know why. I didn't even call sy init. Okay. Yeah, make sure when you're testing this to actually call sy init and sy cleanup. For the love of God, how did I fucking miss that? I did this when I was testing too. I forgot to call this, and I was wondering why the tree was popping up as null. So run this now, and it should be all good. There we go. So we get -1 times the sign times is implicitly added. -1 is implicitly added the sine of 2 times pi times the cosine of 2 times e minus the square root of 22 plus a -1. Perfect. So that works. That's our token parser. Alright, let's do RPN and RPN, or just RPN for now. And then we will wrap up. Alright, so for RPN, we're first going to start by getting all our tokens. And we will use that function. So dynamic array tokens is equal to parse tokens passing the string str. And then we're going to say unsigned integer n is equal to tokens.size. Then we will have our two parallel lists here. So we'll have a dynamic array. Ret is equal to dynamic array allocate, or default allocate. And then dynamic array stack is equal to dynamic array default allocate. So from the Shunting-Yard algorithm, the two structures that we need are a queue and a stack, but this queue doesn't really act like a queue. Well, it, actually, I think it does. Yeah, it will act like a queue when we, holy shit, yeah, it does. Okay, yeah. This queue acts like a queue, when we evaluate it. So I'm going to just rename this as queue instead of ret. Alright, and then before we do anything else, I'm just going to write the last two lines. So dynamic array, free, pass and reference to stack, and then return queue. So we're going to have our for loop in the middle here. So the for loop will essentially just determine how to put the tokens onto the queue in a different, or in a certain order that they iterate properly and in reverse Polish notation. So we'll have a for unsigned int I is equal to 0, I is less than n, I plus plus. Alright, we're first going to get the current token. So sy token pointer t is equal to tokens dot list at I. Then token type is equal to t dot type. Then sy token pointer last stack is equal to stack.size question mark stack.list at stack.size -1, otherwise null. So this line right here means that we want to get the top of the stack. So if stack.size is some non-zero value, then we want to get the last element in the stack, otherwise just put it to null. Alright. So once again, this will come in handy when we want to do the conditions. Essentially this big condition right here. This is going to be necessary. Alright, so now for our switch. We will do a switch on the type. And we're pretty much going to be following this pseudocode to the T. So I will actually just... Oops, you don't want to see that. There we go. So we're going to be following this pseudocode pretty much exactly as it's written. So the first two cases will be constant and case constant string. And these fall into the same case. And this will just be dynamic array, add last, passing a reference to Q and then T, and then break. Alright, so that's this condition right here. Oops, no, don't do that. Then if a function, so case function, we're going to do dynamic array, add the last, and we're going to push it to the stack this time, and then break. Now for an operator, we're going to have our, oops, oh, that was probably very loud. I apologize. I just knocked my microphone. Alright, so for the operator, we're going to have a first condition here. So if stack.size, then we're going to have our massive condition up here. So we will start with the while. So while last stack.type does not equal L_, and then in parentheses, sy is function, and the parameter will be last stack. So the top of the stack can be a function, or sy get precedence last stack is greater than sy get precedence of the current token. So if the precedence of the top of the stack is greater than the precedence of the current token, or then in another set of parentheses we want to say sy get precedence last stack is equal to sy get precedence of t, and sy is left associative last stack. So you should have 4 parentheses at the end here, like that. Oops. Alright, good shit. So yeah, this condition, so it cannot be a left parenthesis, that's this right here. Sy is function, that's here. The operator at the top has greater precedence, good. Equal precedence and left associative is this one. And if it is, we're going to pop from the stack to the queue. So dynamic array, add last, pass in a reference to ret, and we will say dynamic array remove last since it's a stack, and pass in a reference to stack. So we take the element from the top of the stack and remove it from the stack, which is essentially last stack. However, we are formally removing it here. Or this should be a reference to queue. And then we want to update the pointer to the top of the stack. So if not stack.size, then break, and then otherwise last stack is equal to stack.list at stack.size minus 1. Alright, then outside of the if statement, if stack.size, we're going to say dynamic array add last, pass in a reference to stack and t. So once we have popped everything necessary from the stack, we are just going to push the operator to the stack right here. Alright, and then we just want to break out of the case at the end. Alright, then for our left parenthesis, it's going to be a simple push to the stack. So dynamic array, add last, pass in a reference to stack, and then the token, and then break. For case R parenthesis, if it's a right parenthesis, we simply want to pop operators from the stack to the queue until we find its matching left parenthesis. So while last stack and last stack dot type does not equal left parenthesis, then pop from the stack to the queue. So dynamic array add last, pass in a reference to ret, and dynamic array remove last, a reference to stack. Or this should be a reference to queue, sorry. I just misnamed it in my reference, but it is a queue. Then if not stack.size, then break, and then last stack is equal to stack.list at stack.size minus 1, so we update the pointer here. We can actually have a condition here if stack.size, and then put the while loop inside of that and remove the condition for while last stack, because that will be checked for by stack.size 1, and 2, when after removing, if we get the stack.size is 0, then we just break out, so we don't need to check. And then after the while loop, still inside of the if statement, we're going to say dynamic array remove last, pass in a reference to stack, and then break at the end. So we want to essentially remove that parenthesis from the stack, the left parenthesis from the stack. And then if there's something that we do not get, then we're going to say default. We want to free everything, so dynamic array free, pass in a reference to stack, dynamic array free, pass in a reference to tokens, and then return ret, which will be, or return the queue. We don't care what it is. We just found an else, so we don't care what came after. We're just gonna return whatever. Alright, and then outside of the for loop, we're just going to pop the rest of the tokens from the stack to the queue. So while stack.size, pop from the stack to the queue. So dynamic array add last, passing a reference to queue, and then the element to be added will be dynamic array move last, and passing a reference to stack. And then once we're out of here, we also want to free the token list. So after freeing the stack, we can say dynamic array free tokens. Just like that. Alright, pretty good. Yeah, so that's a Shunting-Yard algorithm. Now let's just make sure that this all works. So in main, I will go and get the token list and from the function rpn rather than parse tokens. Alright, and then let's see what our example is up here so we can compare it to an answer. So our input should be sine of 3 to the negative 2 times 27. 27 divided by 4 times pi, or 4 times, or just 4 pi, then close parentheses plus 1. Alright, let me make sure that this will give us the proper result here. Alright, 3 negative 2, exponent sign 27 times 4 divided by pi times sine 1 plus. Perfect. Good fucking shit. Whew. Alright. That's good. That's what you love to see. So yeah, you can go ahead and play around with that shit. I think that's where I'm gonna wrap it up here because the evaluation is gonna take that's a whole, or it's not too long, but I'd rather just include this with our variables because it kind of goes hand in hand with evaluation. And I just wanted to focus this on the Shunting-Yard algorithm pretty much. But now, or next time, we will do evaluation, which could be next week, if I don't work on OpenGL stuff. But yeah, that's pretty much all I have for you guys today. Hope you guys enjoyed. Hope you learned something. And yeah, play around with this, see how it works. And yeah, I will see you guys next time. Have a good one.